So this is question 3, simplex algorithm. A problem to maximise p as a function of x, y and z is represented by this initial simplex tableau. Write down p as a function of x, y and z. Remember, in order to put it into the tableau, you take your p equals function and you rewrite it so that everything is on the same side of the equation. Do you remember that? And that's how you get the coefficients. So this line directly relates, you maybe don't need to write this down, it directly relates to p minus 10x minus 2y, plus 2y plus 3z equals 0. Now that means, if we want p as a function of x, y and z, we're going to write p equals 10x minus 2y minus 3z. And that's our answer for part 1. Okay, so there were 1 or 2 people who forgot that you actually need to change the sign of the coefficients there. You can write that down straight away if you remember. You're just changing the sign of each of those terms. Then it said, write down constraints as inequalities involving x, y and z. Notice we've got 3 marks for this. There are only 2 more lines in our table. That should be a little bit of a clue to us that we've got to be careful with what's going on. So as we do this, well, clearly we can see we've got 5x minus 5z, and there we would have that as being less than or equal to 60. So we can put that one down first. We've also got 4x plus 3y is less than or equal to 100. That jumps straight out of the table. And I've clocked that it's 3 marks. I've got 2 of them. So what am I missing? Non-negativity constraints. We always need to have them in order for simplex algorithm to make sense. So we also have x greater than or equal to 0, y greater than or equal to 0. It feels like trivial, but they are there. And when it says write down the constraints, they're there. They are the constraints. Oh, and z, sorry. Yeah, I've not put z in. And z greater than or equal to 0. So we've got the non-negativity constraints for our 3rd mark. Carry out 1 iteration of the simplex algorithm. I should have taken a copy of the table. Let me just do that. So they gave you, where have we gone? There you are. They gave you a table halfway down your page for you to fill in for your iteration. I would have liked to have seen them giving you that table in the booklet as well, but they didn't do that, did they? So I think most people drew it on the question paper. We need to choose a pivot. We choose the most negative row on the top line. That's got to be it's got to be that one there. Calculate the working values. We're going to do 60 divided by 5 and 100 divided by 4, and we're going to choose the smallest of those 2 numbers. So that is 12, that one's 25. We're choosing the 12. So there is our pivot. And bear in mind, you're not handing that in if you do it on the table in the booklet. So you've got to do at least a little bit of writing of what you've just done there. Show that you've done 60 divided by 5 and 100 divided by 4, and that you have chosen the 5 as being the value that you want out of that. What do we do next? Well, you need to write some instructions about how you're doing it. If I'm calling those rows 1, 2 and 3, my new row 4, 5 and 6 in my table, row 5 is row 2 divided by 5. So that's 0, 1, 0, minus 1, 0.2, 0, 12. I need to use that 1 that I've just generated to make that into a 0. So row 4 is going to be the original row 1 plus 10 times row 5. That gives me a 1 there, 0. 2 plus 10 zeros is 2. 3 plus 10 minus 1s is minus 7. 0 plus 10 0.2s is 2. 0 plus 10 zeros and 0 plus 10 12s is 120. And my bottom row, I need that, that's a 4 at the moment, so this is going to be row 3, take away 4 times row 5. So that's going to be 0, 0, 3, take away 4 times 0 is still 3. 0, take away 4 times minus 1, that's plus 4. 0, take away 4 times 0.2, that's minus 0.8. 1, take away 4 times 0, and 100, take away 4 twelfths is 52. And there is my new simplex tableau for 4 marks out of that. Right, now this bit again, I think there were a few people who got really kind of, you love simplex, so you get into it, you get enthusiastic about it, you get into the simplex zone, and you carry on with this, and you think, right, the next part of the question will ask us to do some more about this. So the question says, after a second iteration, there's a whole new tableau that they're giving us. So it means don't use your answer, ignore your answer. They say this is what happens if you do it again. This is what happens. Explain how you know that the optimal solution has been achieved. Okay, it's quite a neat way of doing it actually if you think about it, because it means even if you do that bit wrong, they're kind of getting you back on track. They're saying this is what would have happened if you'd done it right, and then somebody else had done it right again. Explain how you know that the optimal solution has been achieved. Well, we're always looking at the objective row, the top row, and there's got to be no negative numbers. It's not that they're all positive, because they're not. It's that there are no negative values. So be careful how you phrase that, but all of the values in the objective row are greater than or equal to 0 for part 4. So they are all greater than or equal to 0 or non-negative, however you want to phrase that. And finally, part 5, it says, write down the values of x, y, and z and write down the values of x, y, and z and maximise p, write down the optimal value of p. This is the bit where we're looking, if there's a 1 there, that relates to that number. That 1 relates to that number there. Y is 0, z relates to that 13. Remember, that's how we interpret it at the very end. So that's what we're writing down. P is 211. X is, what did I just say? 25. Y is 0 because there's loads of nonsense in that column. And Z is 13. And there's the answer for the last 2 marks. Easy to make mistakes, but not particularly difficult, I don't think.